Module 7, Part 3 covers simplifying radicals, the Pythagorean theorem, and the distance formula. So please make sure you're completing your guided notes as you go along, especially because simplifying radicals, it's really good to have a whole bunch of examples. So when we're simplifying a radical that isn't a perfect square or a perfect cube, so like for example, maybe the square root of 18. What we want to do is we want to rewrite the number as the product of a perfect square that we could find and the other number, because we're taking a perfect square. So we're taking a square root, so I'm looking for perfect squares. So if I have the square root of 18, I can think of 18 as, if I made a factor tree, 2 times 9, which is 3 times 3. So I can think of that as the square root of 3 squared times 2. And what we want to do is we want to take that square number and bring it in front of the radical. We're taking the square root of that. So that would be 3 root 2, because square roots undo squares. And we leave this other number under the radical. One way to think of it is if you're taking the square root, you only get to go outside of the radical if you have a buddy. And the same would be true for cube roots. So if I had the cube root of 16, we're looking for perfect cubes. So 16 is 2 times 8, which is 2 times 4, which is 2 times 2. So I have 2 cubed in there. So this would be 2 cubed times 2. So I'd have 2 cube root of 2 would be the cube root of 16. So let's practice a whole bunch more of these. So, for example, if I have the square root of 20, we want to factor the radicand. That's what's under the radical. Because we're taking the square root, we want to find the squares. So I know 20 is 2 times 2 times 5, so 2 squared times 5. So I can pull it apart into its factors and rewrite it as the square root of 2 squared times 5. This 2, when we take the square root of 2 squared, that comes to the outside, and we're left with a 5 under our radical. So let's take a look at the square root of 24. The first thing I'm going to need to do is factor this. So I have 24, which is 2 times 12, which is 2 times 6, which is 2 times 3. So the perfect square hiding in 24 is 2. It's just the 2 2's, it's a 4. So I've got the square root of 2 squared times 2 times 3. We can write it as its factors. This first 2 in the front comes to the outside. I have the square root of 2 times 3, so I have 2 root 6, if we're going to simplify that radical. So let's do a bunch more examples. If I've got the square root of 108, I first need to figure out what 108 factors into. So 108 is an even number, so I know it's divisible by 4. How about 2 and 54? 54 is a 2 and a 27. 27 is a 3 and a 9, which is a 3 and a 3. So what perfect squares do I have? I've got 2 2's and 2 3's. So I have the square root of 2 squared times 3 squared times this leftover 3 at the end. And that's all under our radical. So when I take the square root of 2 squared, that becomes 2. The square root of 3 squared becomes 3. And I'm left with the square root of 3. So I have 2 times 3 times the square root of 3. I've got 6 square root of 3. Next, let's take a look at the cube root of 54. I already kind of made most of that factor tree over here. If you just look at the part, I'm going to circle. Okay, I'm going to outline in orange. That's definitely not a circle. I've got 2 times 3 times 3 times 3. And we're looking for cubes. Well, this is 2 times 3 cubed. So I could have 3 cubed times 2 all under the cube root. So my answer would be 3 cube root 2. Now what about 15? Well, 15 factors into a 5 and a 3. There are no perfect squares hiding in square root of 15, so this is fully simplified. If there's no perfect square to take out of a square root, it's fully simplified. What if I have the cube root of 16? I believe I did this example a few slides ago, but we can do it again. 16 is 2 times 2 times 2 times 2, because it's 2 to the 4th. I've got one perfect cube hiding in there. So I've got the cube root of 2 cubed times 2. So I have 2 cube root 2. For problem 6, I've got 16 again, which I know is 2 times 2 times 2 times 2. And I've got an m squared, which factors into an m and an m. So where are my perfect squares? Well, 2 squared, and m squared. Those are all my perfect squares. So I'm going to have the square root of 2 squared times m squared. And since everything's a perfect square, all of them come outside of the radical. So I'm left with 2 times m, or 4m. For 7, we can kind of tie it all together. I've got the square root of 16. Well, we know the square root of 16 is going to be 4, but now I've got m cubed. So I've got 16, 2, 2, 2, 2, m, because I have m cubed. Well, that means I'm going to have 1m left under the radical. That's how this problem, ooh, excuse me, that's how this problem changes. So we'd have 4m square root of m. Because for this example 7, I'd still have an m under the radical. Let's look at the square root of 200 k to the 7th q to the 8th. So again, I'm taking the square root. I'm looking for perfect squares. 200, that becomes 2 times 100. Well, 100 is 10 squared, so if I want, I don't have to break it down much further. And then I've got k to the 7th, so I've got 7 k's. And if you can see how this is going to factor without doing all of this, good for you. That's a really good habit to get into. But just because we're starting, maybe we can't. So now I have 7 k's and 8 q's. So I'm collecting all the perfect squares. So I've got 10 squared, 3 k squareds, and 4 q squareds. So what's going to be left? 2 and a k is what's going to be left under my radical, because they don't have any partners. So I could write this whole thing out, right? So I've got 10 squared times k squared times k squared times k squared times q squared. You don't have to do all of this if you can already see how this should simplify. So I'm left with 10, 1, 2, 3 k's, so k cubed, 1, 2, 3, 4, 4 q's, square root of 2 to the k. For problem 9, again, I'm looking for a cube root. Well, the cube root of -8, that's going to be -2. But how do I deal with x to the 4th and y to the 5th? Well, if I have 4 x's, I've got one perfect cube. And if I've got 5 y's, I still just have one perfect cube and 2 left under the radical. So I'm going to have -2xy times the cube root of xy squared. We're going to talk about multiplying square roots. So if a and b, there should be a space here, are real numbers and n is a natural number, i.e. we're taking a positive root, then it's always true that the nth root of a times the nth root of b equals the nth root of a times b. Basically, we can multiply what's under our roots as long as we're taking the same root. So if I had the square root of 2 times the square root of 7, that would be the square root of 14. But if I had the square root of 2 times the cube root of 7, this can't be simplified any further because a square root isn't the same as a cube root. So this would be fully simplified. So let's do a bunch of examples and make sure we're remembering to simplify our square roots and our cube roots. All of our radicals need to be simplified. So 5 to the square root of 5 times the square root of 15. I'm going to take the square root of 5 times 15. That gives me the square root of 75. And now to simplify this, I look for perfect squares. 75, well, that's 3 times 25, which is 5 squared. So I'm going to have the square root of 5 squared times 3. So 5 square root 3 would be my final answer. I recommend simplifying your radicals first if you can. So I couldn't simplify the square root of 5. I couldn't simplify the square root of 15. And then I multiplied them. And that's because when you simplify them, you get a smaller number under your radical, so it makes it less work. So for instance, if I have 3 square root of 8, well, 8 is 2 times 2 times 2, so that's one perfect square. I'd have 3 square root of 2 squared times 2, so that's 3 times 2 root 2, times, well, the square root of 4 is 2, 2 times 2, 4. So I have 3 times 2, so 6 root 2, and we're going to multiply that by 4. Well, we're just going to multiply our constants in front of our radical. So I've got 24 root 2. Let's simplify the square root of 32. 32, I know that is 2 to the 5th. So it's got 2 perfect sets of squares in there. So that's going to be negative square root of, we could write this as 2 sets of 2 squared, or I could write this as 16 times 2, which is 4 squared. My 4 is going to come out, so I have negative 4 square root of 2 times 5 square root of 2. That gives me negative 20. Square root of 2 times the square root of 2 becomes the square root of 4. The square root of 4 is 2. So I have negative 20 times 2, negative 40. Final answer. All right, so now I have 4 square root of 5 times 3 square root of 7 times the square root of 5. And one thing I'd like us to pick up on is if I have the square root of 2 times the square root of 2, that becomes the square root of 4, which is 2, right? This is like I've got 2 to the 1/2 times 2 to the 1/2, which is 2 to the 1st, which is just 2. So if I've got 4 square root of 5 times the square root of 5 times 3 square root of 7, I can rearrange this by our associative property. This times this is going to give me the square root of 25, which is just 5. So I have 4 times 5 times 3 times the square root of 7. 4 times 5 is 20 times 3 is 60. 60 root 7 would be my final answer. For problem 2, I have 10pq squared times the square root of 2p squared q squared. This q squared is a perfect square. It's going to come to the outside. So I've got q square root of 10p times, this 2 is going to stay under there, but I'm going to have a p come to the outside. And I've got q to the 4th, which would give me q squared on the outside. Root 2, now I can multiply together. Remembering we multiply our constants and we multiply our radicals. So I'm going to have q times pq squared, so that's pq cubed. Square root of 10p times 2 would be the square root of 20p. And then I can simplify the square root of 20 because 20 is 4 times 5. So I have pq cubed square root of 2 squared times 5 times p. So this 2 is going to come to the outside. So I'll have 2 in the very front because we like our constants in the front. Pq squared square root of 5p. That ended up being more complicated than I thought it was going to be. For problem 3, I've got the cube root of 9y times the cube root of 6z to the 4th. If I've got z to the 4th, there's definitely a z cubed hiding in there. So I'm going to have the cube root of 9y times z cube root of 6z. And I can multiply what's under the radical. So I've got 9 times 6, which is 54. So I'm going to have z cube root of 54 yz. And we already found the cube root of 54. We know there's a 3 hiding in there because, sidebar, 54 is 27 times 2, and 27 is 3 cubed. So I can rewrite this as z cube root of 3 cubed times 2yz, and that 3 will come to the outside. So I have 3z, 2y squared. We're taking the cube root of that. So that would be my final answer. Here are our final answers for these problems. Last example, I have negative 8 square root of 10m to the fourth times 2 square root of 5m. I can simplify this m to the fourth, so I have negative 8m squared square root of 10 times 2 square root of 5m. I multiply my constants. I multiply my radicals. That should be a 50. The square root of 50, well, that's 50 is 2 times 25. So I'm going to have negative 16m squared square root of 5 squared times 2. So negative 16 times 5, that's going to be a negative 80 m squared square root of 2. The last two topics we're going to cover are the Pythagorean theorem and the distance formula. And these are two mathematical models that we can use that require us to know how to work with radicals, primarily square roots. So the Pythagorean theorem says if I have a squared plus b squared equals c squared, that's going to always hold true for a right triangle, where c is the longest side. This is also called the hypotenuse. Spelling is questionable, right? But we call it the hypotenuse. So we're going to have this formula. A and B are the other two sides. It doesn't matter which one's A. Let's let 4 be A and 6 be B, and I'm trying to solve for C. You might have seen this in a geometry class as well. So I'm going to take 4 squared plus 6 squared equals C squared. I'm trying to figure out what C is. Well, 4 squared is 16, 6 squared is 36. 16 plus 36, that's going to be 52. Well, how do I get this c squared all by itself? I'm going to have to take the square root. And since we're measuring a length, we really only need the positive square root. So I've got the square root of 52 is c. Well, 52, that becomes 2 times 26, which is 2 times 13. So I have the square root of 2 squared times 13 is c. So I've got 2 square root of 13 is c. That would be the length of our hypotenuse. For the distance formula, this goes back to what we were doing in modules 2 and 3 when we're working on graphing on the Cartesian plane. So if I have 2 points, x1, y1, and x2, y2, so let's say I've got any 2 points on our Cartesian plane. So here's our x-axis, here's our y-axis. I can find the distance in those 2 points by taking the difference in x's and the difference in my y's and taking the square root. I'm essentially finding the hypotenuse. So squaring those to make it positive and then taking the square root. So for example, if I have my distance is the square root of x2 minus x1 squared plus y2 minus y1 squared, I label my points x1, y1, x2, y2, and then I substitute. Distance is the square root of 3 minus a negative 6 squared plus negative 4 minus 5 squared. So distance is the square root 3 minus a negative 6, that becomes 9 squared, plus negative 4, negative 5, that's negative 9 squared. My distance would be the square root of 81 plus 81. So my distance is the square root of 162, which I can then simplify because 162 is 2 times 81, and 81 is 9 squared. So this would simplify to 9 root 2. So now that we're working with radicals, we always have to make sure we are simplifying what is under our radical symbol.